Good morning, everyone. I'm Lao Tin Wai from Ching Middle School. Today, I'm going to present my project concerning on Mortet equation. So, given integer k, the Mortet equation is the differential equation of the form as shown. Notice this the differential of two variables, and the natural number theoretic task is to find all integral solutions of this equation. So the newest numerical results are all solutions for k satisfying this inequality have been found, and general results of elliptic curve have suggested that there are only finally many integral solutions. And in 1968, the Baker have shown that there exists theoretical bound for x and y to compute all integral points. However, there is still no known effective algorithm other than exhaustion using the Baker's bound. So what I've been thinking of is that this equation have not only properties in elliptic curve, but also beautiful insights for some algebraic insights for some classes of k. So in this project, I'm only considering classical approaches, and we derived some nice result as shown. So the first section is factorization in Z. Firstly, I think of is we let some k special cases of k such that some factorization can hold. For example, if k is a square number, then using the difference of two squares identity, I can factor it out. And the motivation is if y plus m and y minus m are relatively prime to each other, then they are both keeps. Using this intuition, I can derive the main results, solving k as a perfect power of 4. To prove this theorem, I'm going to present three lemmas first. The first lemma is equal k equal to 1 case, which is strictly follows from the Cartesian conjecture. Notice Cartesian conjecture only works for x, y are positive integers bigger than 2, so there's still some technical work required, but they are easy. This next lemma is k equal to 4. Firstly, notice that y equal to 2 mod 4 and 4 divides x, so I can write this equation as shown. And as m and m plus 1 are relatively prime, so this boils down to solving the differential equation. U keep minus 4 3 keep equal to 1. And we claim that this equation has no non-trivial integral solutions, which is u is equal to 1 and 3 equal to 0. To prove this claim, I'm going to develop some tools of the cubic number field first. Firstly, I can compute the norm of the element, which is using this formula. And notice the fact that if the norm of an element equal to 1, then the element is a unit, which is invertible. Nextly, by Dirichlet unit theorem, the group of units are finally generated, and this can be expressed by this form. So I can turn back to our attention. The proof is, notice that u minus 3 to the square root of 4 is a unit, so I can use Dirichlet unit theorem to express it as shown. If g is bigger than 0, notice that the right-hand side must consist of a cube root of 2, so which contradict to the left-hand side. So there's no integral solution. Similar for g is more than 0. So g equals 0, this corresponds to x, y as 0 and plus or minus 2. The next lemma is k equals 16, which is straightforward using the motivation. Now I can prove the main theorem. Notice that the three lemmas are presented as special case of theorem here are where n equals 0, 1, 2. And the proof, I'm going to reduce the equation into three lemmas presented. Notice that 4 divides x and x divides y, so I can write this equation as shown. Notice here n is subtracted by 3. So by diffusion algorithm, I write n equal to 3k plus r, and repeating the process of subtracting 3, I reduce the equation as shown here. Notice n r are smaller than 3, so this one of three lemmas I saw, and the result follows. So the main result here is I obtain all solutions for k is a perfect powers of 4. Notice there is just a small classes, so I will going to employ other methods to solve a bigger class, which is section 3. During this time, I set qk as a m cube minus k1. The equation becomes this. The method is I choose a suitable prime p such that the equation has no solution. How to choose that? Okay, by the theory of conjective residue. Firstly, I find a prime factor in here, x squared minus mx plus m, and use lemma 3.1. I can deduce a congruence condition on P as shown here. If P doesn't satisfy the congruence condition as shown here, then this we have the equation has no solutions. I will illustrate my method using position 3.3. So notice that we can write this equation as shown here. And then because x equal 1 mod 4, So this has this will be equal to 3 mod 4. So there exists a prime factor p in here such that p equals 3 mod 4. Or else all prime factors are equal to 1 or 2 mod 4, which won't result into 3 mod 4 in general. So however, since y squared plus 4b squared equals 0 mod p, then by lemma 3.1 we have p equal to 1 mod 4, which we derive a contradiction. This using the similar ideas, obtain the main result here as shown. Notice this class of k are substantially improved, but this method only works for proving that the equation has no solution. So I want to find other non-trivial solutions, so I obtain the section 4. We are forced to consider the factorization again. However, this time I'm going to factorize in the number field q square of k, and the integration is if y plus square root of k and y minus square root of k are relatively prime, and the number field q square root of k are unit factorization domain, then they are both keeps. Notice in my project, I only consider the factorization in Gaussian integers. However, I have to stress that this method actually holds for general number field. Indeed, actually there's some literature concerning on this idea can derive this theorem as shown. However, in my results, I'll actually obtain k as a difference condition of this theorem, which is different to other literature. So this is theorem 4.2. I consider k equal to minus p squared, where p equal to 3 mod 4. Here is an example. Firstly, I factorize this equation as shown here, and we are going to show that y plus pi and y minus pi are relatively prime. Let delta be the common divisor among them. Then delta must divide the difference, where norm of delta will divide 4p squared. On the other hand, norm of delta will be divided an odd number, so the only possibilities of norm of delta are 1p and p squared. And we are going to prove up the possibility of p and p squared. If norm of delta equal p, then I can write p equal to a squared plus b squared, which is impossible. For p squared, using the Pythagorean triple generator, I can derive the equation as shown. And consider later equation, notice g equal to 1 or p. So if g equal to 1, then actually I can write it again as a sum of 2 squared, which is possible. If g equal to p, then p divides both x and y. So I obtain this equation as shown. And then consider mod p, and minus 1 will be a conjective residue mod p. However, this is impossible again as p equal to 3 mod 4. So we have norm of delta equal to 1. Notice in Gaussian integers, every unit in the Gaussian integer are keeps. So I can write absorb into keeps here. And I'm creating the real and imaginary part, and we get this form. Notice in here, n is a factor of p, so I'm going to analyze the 4 cases, n equal to plus or minus 1, plus or minus p, as p is a prime. In here, notice that p equal to minus 1 and p equal to p are impossible considering some properties of the equation. And n equal to 1 and n equal to minus p are actually, I can find two solutions. To prove they are mutually exclusive, we can write p as the p satisfying both conditions, where I can write it further to be a sum of 2 squares, which is impossible again. In here, I can generalize it to my more general theorem, where in here, k is a product of distinct primes, where the primes are equal to 3 mod 4. And here is an example where case 77, I actually have to check the 8 cases, and there are none of them satisfying this condition. So this equation has no integer solution. So in conclusion, in section 2, I consider factorization in set, where I obtain the main result of k is a perfect power of 4, reducing into 3 lemmas of n equal to 0, 1, and 2. In section 3, I consider conjugate residue, so I prove some of the classes of k has no solution. And at last, in the section 4, I consider factorization in Gaussian integers, which I obtain that k equal to minus p squared, where p is 3 mod 4, has the solutions I presented. And actually, I can generalize this theorem into a product of distinct primes, where the primes are all 3 mod 4. This is the reference, and this is the end of my presentation. Thank you.